In feature engineering, we have created lag features, cyclical encoding and rolling statistics, and we have seen the code and reasons for doing it. So after feature engineering, we split the data, and we have also got to know why we have used chronological train test split and the time series split for the training set, and why not the k-fold. So after feature engineering and data split, now our target is standardization. But why standardization? When we create new features, we mix variables of different units. Let's take our example. So here we have date time, float, int, and string, right? These are the types. But when I say different units, it is like the temperature max will be in degree Celsius, rainfall will be in millimeter centimeter, then the speed will be, wind speed will be in numbers 1 to 10. So these are all continuous numerical features with the different scales, right? If those are not scaled properly, these features, if it contains larger ranges, it will definitely dominate the model. So with scaling all the features, we can make them to contribute fairly. Okay, so let's see some common standardization techniques. First is standard scalar. The common formula z is equal to x minus mu by sigma. This will represent the data with how many standard deviations it is away from the mean. It will subtract the value with the average value, that is mean mu, and divided by the standard deviation, that is the divided by the variable spread. Okay, this works very well with normally distributed data, and one thing to notice, it is sensitive to outliers. So this is called z-score normalization. So it will alter our it will scale our feature values to have a mean of 0 and standard deviation as 1. Next, so the second one will be the min-max scalar. This is a formula which we will have min and max of x values. This will map the lowest point to 0 and highest point to 1, so that the range is between 0 and 1, and it will smoothen the values in between. This is useful when our features are constrained to a specific range. The third will be the robust scalar, where we will be using median and IQR instead of mean and standard deviation. This is better for skewed data, and this is resistant to outliers. Also, this min-max scalar is also sensitive to outliers. So one important thing to notice, we have to choose the scalar based on our data distribution and the problem we are solving. Okay, so now why standard scalar? So we didn't try it with min-max scalar, robust scalar, because weather data is like it is a normal kind of distribution. So we are keeping it simple, and usually do not contain extreme outliers after pre-processing. Even we can see here, this is the max column. So we don't see any kind of very much values in extreme level, so that we can consider it as outliers. So usually standard scalar will expect numerical columns. One thing before moving on, we have weather code, right? So this is in object. Okay, so what happened was, okay, here to understand YAML file, we mapped the weather code to the weather map, and we changed it into the string column. So this is not needed. We will keep it as categorical variable in numbers, and we will later encode it and use it for our modeling purposes. So for that, instead of changing everything, I will send the request and get the data again. Fine. Okay, we got the weather. Okay, still it is int. Now I will change this to raw, so that I can avoid running it unknowingly. Okay, now doing the feature engineering. Okay, now our weather is same as integer. Okay, data split. There is no need of changing these visualizations because we didn't use a weather variable here. Next will be can see a difference. See, feature df will have, okay, now this is an object, now it is an int. Okay, this is to ensure that we are keeping the weather code as it is and we can extract it later. Okay, now, okay, so the next question is, we saw why standardization and it only accepts numerical features. Then comes the question, why standardization? Why we are performing standardization after feature engineering? Why not before? One simple explanation. If we calculate the mean and standard deviation on the entire data set before splitting, the information from the test set will leak into our model, leading to overfitting, which is a very much serious problem. So any feature engineering step will change the scale of our data all over again, right? So it is not that we are creating something will not that will have the same scale. So we will be combining columns, we'll be creating much more different columns, taking transformations, sine, cosine transformations, everything, so that our entire data set will change, right? So we will end up having to standardize again for the second time anyway. That is not a standard way or the right way to do, right? So this will distort the true relationship with the data once we are feature engineering a standardized one. Okay, so this will clearly distort the true relationship or data. We cannot bring the actual data to the model. So to standardize our data correctly, we have to always fit the scalar only on the training data and then apply those same calculated parameters to transform our test data and future production data. Okay, so this is why first we did the feature engineering, then the data split, then comes the standardization part. And this standardization, we have to there is two things to understand: fit and transform. We have to fit and transform the training data, and we have to transform only the test data. And for that we have to create the the scalar. So we will code standardization. So first sklearn, it is under pre-processing. Import standard scalar. Okay, I'll create two more. Now scalar, I'm creating an object standard scalar. Let's see what scalar has now. Okay, so one thing to note, we'll take the extrain.info. Here we have mixed data types, not the scale, now the data type. One is date time, one is int, float. Okay, these are different things. Int and float, they come under the numerical column, but date time, it will not. Okay, so standard scalar works with numerical types. So it will try to convert all to a single numpy array. But this date time cannot be changed to float automatically. So we can either drop it or encode it. Data is an important feature. Will it be reasonable to drop the date field? Right? Will it be reasonable? I think no, because date is very much important. But one thing to notice, with the date, extracting the number of days, here we have done the cyclical encoding, right? So date will have an effect on that. Also, as it refers to the season, we already have that cyclical encoding that tells us the season from the date column only. So it is better to drop date. If we didn't do any kind of encoding and only relying on date field, means we have to keep the date field. Other than that, if we have done something with that which represents the same thing, we can drop the date column. Now we have the cyclical encoding with us. So this month, week, day of year, day sign, day cause. So we can drop the date column. It is safer to do so. Okay. So we will drop the date column. from xtrain and xtester. Okay, drop of columns equal to date, dropping and saving at the same time, so in place true. Next, xtest dot drop of columns equal to date, in place equal to true. Okay, now for our project we are using different regression models that needs different pre-processing strategy. So what we are going to do is, we are not going to pre-process now, we are not going to scale our data now, because pre-processing should depend on the algorithm needs rather than forcing particularly one pre-processing strategy for all the models. Okay, since pre-processing requirements differ across algorithms, we will first save the generated train and test data sets. Then during the model training, we can apply model specific pre-processing such as standard scalar only wherever necessary. So this will keep our pipeline modular, and it will prevent unnecessary transformations and enable fair comparison across different models without forcing one pre-processing strategy. So we can save our split data, unscaled data and scalar. So before doing that, we need to understand two things. One is JOBLIB and PKL file. JOBLIB is a library, and PKL file, we will see what those are. Okay. Dot pickle file. Okay, this is a byte stream file created by Python's pickle module. This is used to save Python objects like list, dictionaries, or even machine learning models directly to our hard drive. So this is called serialization or pickling. So once it is saved in the hard drive, we can load the file back into the memory, and this process is called deserialization or unpickling. So JOBLIB can save models with .pkl extension, so they will work together, and we are going to make it work together in our project. How we can call is joblib.dump. If you are saving the scalar, I can call the variable comma, and we'll specify the path and the file with an extension .pkl. Okay. Now this first we will save our x train and test, y train and y test. Then we will come to the pickle file. Okay, so first is, I have my x train, x test, y train and y test. Okay, also I have created a helpers file inside utils. So inside utils I have created helpers file. Okay, so here I'll have the common things where I can reuse it with every other notebook. So here I have my base directory, then the data directory, models directory and plots directory. So in our, I'll create a new cell. In our notebook I will use import utils. Okay, so from utils dot helpers import models directory, then the data directory, because we are going to save the data and the scalar model, right? So I'll call both data directory to save our xtrain test data, and models directory to save our pickle file. So first we will see two ways of saving. One is assigning columns. What if they have different column names? That is, what if they are not aligned in the same manner? What if train and test data has all the columns common but not in a particular order? So pd dot data frame, I will take the xtrain and have the columns as xtrain dot columns. So it stays along with that xtest pd.data frame, we are making sure we have the right column names equal to xtest dot columns. So you can give your order anyway, anything you desire, and I'll convert this into CSV using dot to CSV. Also there is one thing, OS. Okay, so now I will join the path of my data directory with my file name. So that will be os.path.join, which is our data directory, comma xtrain.csv. Okay, this will be our file name, comma index will be false, right? Okay, the same goes for xtest dot to csv, os.path.join in the data directory with the file name xtest.csv, comma index equal to false. Okay, next another way of doing is directly saving the variable. One is ytrain dot, I'll remove this, we are saving it, so no need of having a variable. See, another thing is directly saving the variable, that is ytrain dot to csv of os.path.join data directory, then comes the ytrain dot csv, comma index equal to false. The same to csv next. Okay, everything is saved. We can go to our folder. We have got our test and train sets accordingly. So now okay, so we have saved our data set, and one more thing we have to do is we have to save our scalar, right? So for this we need to understand input JOBLIB. Okay, so JOBLIB has this joblib.dump, where we can have a scalar and use models directory, comma scalar.pickle. This will be the file name with the extension pkl. Okay, so okay, done. So we can go and see models. Okay, we have the scalar.pickle. So saving the raw and unscaled data, and we will perform the scaling inside the model notebook. In this way we can rerun the change, rerun or change the scalar if needed. So we can apply the same scalar.pickle and to keep the pre-processing and modeling separately. Okay. See, we'll come for the weather code later. So the models we have desired is linear regression, ridge regression, lasso regression, random forest, and XGBoost. Okay, so what are we going to do with the weather code? Because it is a categorical data, we have to encode it, because the model should not see it as a continuous numerical variable, right? So our weather code is numeric, but it is categorical type. But standard scalar, what it will does is, it will change the numbers, consider it as continuous, and scale it with mean 0 and standard deviation 1. But this is incorrect with respect to the weather code column, because weather code is a categorical variable, not a continuous measurement. Weather code categorical, it should be one hot encoding. We should do only one hot encoding. So for that we can choose pd.getDummies for the columns weather, and same in the test. So this will create one hot columns for each and every categorical available in that particular column. So during this time we need to ensure whether our train and test have identical columns, and we have to create numerical columns list. So this should exclude one hot columns. Even though it is a numerical column with zeros and ones, we should not include it in the numerical columns, because this numerical columns list will be used for the standard scaler and other pre-processing methods where numerical columns are only needed. So next, on scaling only the numerical columns, extrain scaled will be extrained dot copy, because we have to take a copy and keep it beforehand, because we have one hot encoded columns also. We need that too for the model prediction. So what we will be doing is scalar dot fit transform the extrain numerical column with the, this is a typing mistake, sorry, extrain scaled for the same column. So only we will fit transform the extrain numerical column values to the extrain scaled numerical column values. So the values will be scaled, but one hot encoder columns will remain untouched. Okay, during training the model will receive both standardized numerical features and the one hot encoder categorical features. So the numerical values are scaled to improve optimization, while binary one hot columns are kept unchanged because they already have meaningful values of 0 and 1. So this is about the weather code. Why I am telling here is we are not going to standardize now, but we are going to see a visualization where we will be seeing the correlation between the variables. So for that we will be having the same, because we are going to scale that and we have to see that. So we have to avoid the weather code. So we will see how to avoid the weather code and scale the other columns and try to visualize it for the correlation matrix purpose. So we'll see. First we have to get the numerical columns, that is extrain dot select D types will select all the data types that includes number. Okay, I'll take those columns to list, so that my numerical columns will look like this. Okay, see here weather is there because int. Now we are going to take a copy of train and we'll store it in extrain scaled variable. Next, extrain scaled. Now only we are going to choose the numerical column values, that is these column values, right? We are not going to encode weather column now. We are just going to treat weather as it is. Okay, we will see one hot encoding during the modeling time, but here we will take weather as it is, the code numbers. Okay, now scalar dot fit transform extrain of numerical. This will also select that those particular numerical columns and perform the transform and then fit it to the extrain scaled numerical column values. Okay, so during the scaling time we are using fit transform, right? So we need to understand what is fit, what is transform, and what is fit transform, and why we will be using fit transform for only train and why not for the test. Okay, fit method learns the parameters from the data So this will calculate our mu and sigma, that is respect to the standard scalar. Okay, now when we fit x-train to the scalar, so that the scalar will know how to standardize the future data. Okay, it will learn mu and sigma values. Just it will learn, it will not do anything, it will just get the mean and the sigma values from that, from the data. Okay, so we can also see scalar dot mean underscore scalar dot scale underscore. Okay, with this we can get the values. Next, using only transform, this transform will not work standalone without fit method. This uses values learned from during the fit method to scale the data. So what it learned was mu and sigma. It will apply it to the formula and get the output. So it will not create any other new variables or something like that. It will just take the mu and sigma from the fit method and directly apply it to the formula and give the values. Okay, so this will be done using the fit learned parameters. Okay, next, fit transform, together fit plus transform. Okay, so why fit transform in X-train? We will be using the fit transform method for the training set. This is because the training should determine the scaling parameters, because testing should not do that. Why means scalar or transform X test, this is what we will perform. But while using fit transform for test, this will create another mu and sigma that is not based on training but on the testing set, right? So this will be the data leakage. Okay, since info from the test influence our pre-processing, that's it. So our parameters, the scalar should learn the parameters from the training data set. So we'll be using the fit transform for the training set and the transform for only the testing set. Okay, given that, let's see how our X-train scaled turned out. Okay, okay, now this is a correlation matrix. Okay, we are going to see correlation matrix. So for that we'll have another picture. Correlation matrix gives the correlation between all the possible pairs of values in a matrix format. Okay, this tells us the relationship between two variables here, A and B, A and C. So this will tell the relationship strength between variable A and B. Okay, if it is 1, it has a strong positive relationship. If it has 0, there will be no relation, that is there exists no relationship. And -1, this is a strong negative relationship. Okay, so this is a correlation matrix. So during visualization we can visualize it using the heat map. This is a 2D visualization of a correlation matrix. So the color intensity indicates the strength and direction of relationships between multiple numerical variables. Okay, so this line, if we notice, this diagonal line will be 1. So this is a perfect correlation because A is correlated to A itself. If this number is less, then there is something wrong with the data. B is totally correlated with B, C to C and D to D. So this in that way the diagonal elements will be the same. Okay, this is what correlation matrix, and heat map is done using the correlation matrix. We will see how to visualize that. We have matplotlib okay already, so I will just import my seaborn. Okay, now I'll just take data frame. Okay, let's see. Okay, I'll take the X-train scaled, copy to I'm going to plot, so df plot. Now my df plot of target will be my y-train, right? See, df dot, we we are constructing our complete data frame. Okay, we are not going to leave the predictor variable also, sorry, target variable also. Now see the target here. So we have the temperature here. Okay, so what we did was we took the X-train scaled data and Y-train and combined it to a new data frame. Okay, so simply pl dot figure will give the fig size 12 comma 5. I think we need something more, 12 comma 14. Okay, let it be. Correlation, that will be dfplt dot corof. You have to call the corof method. Now sms dot heat map this correlation matrix, and we will use cool warm. When you check with the official documentation, you will have different types of color maps and different parameters also, so you can use anything. So and not is equal to true, so that these numbers will stay intact, and I will keep the decimal with 2 points, then the line width to be 0.5. Okay, then obviously a title, correlation heat map. Okay, let's specify the size 14 maybe. Wait, I'll bold it also, small letters. And I will show. Let's see whether we have any kind of spelling mistakes. Okay, this has to work. This beautifully colored map. Okay, we will reduce this. Still not visible. Okay. See, weather to weather, high correlation, and it also gives us the correlation between all the other variables with weather. Okay, so let's take weather, and the correlation with temperature max it is 0.39, and along with that you can see all the correlation values. So leaving the numbers, you can also use the colors to find the intensity. Okay, month and day of the year is very well correlated, and temp max, we have temp max and temp min obviously, and lag features have a good kind of relationship with the temp max because they have been created from that, the lag features, right? And the target is also the same. So this is a correlation heat map, and this explains the relationship between our variables. So next so we have our scalar pkl file, then our train test csv, and our models. First will be linear regression. Okay, so we will perform this like we will use the scalar and the train test datasets in all our models, and we will standardize it based on the model requirements. If it is needed, we will standardize it, otherwise we will not perform any kind of pre-processing. So following linear regression, we will go through ridge regression, then lasso regression, 4 will be random forest, 5 will be XG boost. So these are not going to be a dumb explanation that I have given like now. We are going to see some exact math and how different things, like we will be visualizing different kind of parts of the models, and some pre-processing steps, and how to make use of the helper file, like getting function from a common and reusing it for all kind of models and saving the best model. And we will be also using grid search CV and much more. So happy coding. Let's see in the next video. Thank you.